Hi, welcome to this third video in my series on introductory data science with R. My apologies for the long hiatus between the first two videos and this third video. To be honest with you, I didn't actually expect to get the number of views on YouTube that I've gotten so far. So I've decided to redouble my efforts to complete this video series as I originally envisioned, and hopefully folks will continue to get value out of what I'm doing here. Okay, with that being said, just a couple of housekeeping things. First and foremost, I need to mention that since the last video was made, I've upgraded both my Mac OS as well as R&R Studio. So things will look a little bit different than the last video, but it shouldn't be anything difficult to reconcile. So just for the sake of completion here, you can see this is the version of R I'm running right now, which is 3.22, and that's right, there we go, on the Mac, and I'm running version 0.99.489 of R Studio, just in case you want to upgrade your system to be the same as what I have here. Okay, that being said, all the code for this series is up on GitHub. What I'll do here is just quickly run all of the code from the first two videos, and you'll see here it's generating a bunch of code and a bunch of plots. You can go check out the first two videos if you haven't already seen those, or review them if necessary because of the long hiatus between the second and third videos to understand what's going on. So just to recap, in video 2 we started going through data analyses for the Kaggle competition related to the Titanic. This is an introductory competition on Kaggle. It's constantly ongoing, and I highly recommend it to everybody that I mentor getting into data science to give it a try, because the data set is relatively small, it's relatively straightforward, but it's still a relatively complicated problem to get right or to do well on in terms of accuracy. It is a classification competition, so it's the stuff that you learn by executing on this competition is useful to a wide range of business problems. Everything from fraud detection to customer segmentation to you name it. I mean, there are many business problems that are amenable to a classification problem. Okay, so that being said, these are the data points that are available in the data set. And through video 2, we covered data analysis of all of the highlighted variables in the data set. So what we're going to pick up with is these last 4 and just close out the initial pass through the data. And then in subsequent videos, we'll go back through and do more detailed analyses to try and figure out of the data elements, the data variables that we want to keep, how do we potentially improve upon those, and then get to actually training a model to see how well our data analysis and feature engineering efforts were successful. Okay. So we need to take a look at the ticket variable. So the first thing that I like to do when I'm looking at a variable, here I'm going to maximize this, is just do a quick str. The str command, and as always, don't hesitate to use the help system. And as it's indicated here, this is all about just saying, look, what is this data item, this variable in R? What's the structure? That's what str stands for, structure. So you can see here that ticket, as currently represented in the combined data set, is a factor variable with 929 levels. That strikes me as not being truly a factor variable. With 929 values, it's unlikely that that's the case. More than likely, these should probably be treated as string variables. So that's what I'm going to do here. You see in this line of code here, I'm going to go ahead and take the ticket portion of the data.combine data set, and using the as.character function, and as always, now you can see here, this is one of the things I wanted to mention in RStudio. The newer versions of RStudio has what Visual Studio calls IntelliSense, which is great. And you can see here, this is just, according to the documentation, right? It just transforms things from whatever representation they are currently in into a string or a vector of characters or an array of characters. So I'll go ahead and execute that and say, look, take the ticket, take essentially the factor level. As you can see here, the factor levels in fact strings is indicated here by the double quotes. Take each one of those, convert it away from a factor into a string, and then cram it back into the ticket variable. This has the effect of just transforming the factor to a string. And just in case, we can go ahead and run this code up here if we'd like, and just run that again. And you can say, okay, now it is an array of arrays. So 11309 of various characters. Great. So to get some sort of flavor of what the data looks like now, we can just ask R to give us the first 1 to 20. Remember that R, unlike other programming languages, indexes from 1, and this syntax here tells R, hey, for the ticket variable on the data.combine data frame, give me the indexes 1 through 20. So spit out the first 20 strings. And you can see that down here in the output. Now, the first thing that strikes me by looking at this data is there's not a lot of structure in it, right? We've got some numbers, and we've got some letter prefix codes of various kinds. And to be honest with you, without being an expert in how at the time the shipping cruise line that ran the Titanic decided to create their ticket numbers, I have really no idea what any of this means. So as a data scientist working with data that is unknown or doesn't have good metadata with it, sometimes you just kind of have to play around with it to see what kind of structure that you can get out of it. So one of the first things that strikes me is though I could probably just grab the first character of each one of these, the A's, the 1s, the 3s, the P's, the S's, and just take a look and see if anything at all pops out at me. So I can do that pretty easily with one line of code. This is where the power of R really starts coming in. Once you get used to the syntax and the functions, you can do a lot of really cool stuff in very few lines of code, as opposed to an imperative language like C++, C#, or Java. Okay, so what I'm going to do here, I'm going to unpack this one piece by piece so that you can understand it. So the first thing I'm going to do is I'm going to grab the substring. Now this is a function, and again, don't hesitate to use the R help system. It is your friend. So substring is a built-in function which allows you to create, pull out chunks of a string. Very common if you've done any sort of programming at all. Sure, you've done this before. So this function will grab the ticket and say, hey, starting at position 1 and going through position 1. So start at 1, stop at 1, give me the first character, pull it out, and return that back out to whatever I want to do with it. Now, the thing to remember is with most functions in R, these functions are vectorized. So this function is smart enough to know that what it's operating on is not one string, but a whole bunch of strings, 1,309 strings to be exact, because as we can see over here, data.combine is 1,309 rows or observations, right? One of which of these 13 variables just happens to be one called ticket. So this is great because what it allows you to do is you don't have to write for loops all the time like you do in other languages to iterate over all these things. Python, of course, has ways around that, but the classic languages like Java and C#, for example, you have to write a lot of for loops. Okay, so grab me the first string or the first character out of all of the 1,309 strings that are in the ticket variable on the data.combine data frame. Okay, return that back. Okay. Well, here what I've got is that the substring call is actually wrapped in an if-else. And as always, so if-else is just basically a ternary operator. So it's equivalent to question mark colon in languages like Java, C#, and C++. It just allows you to do an if-else test. And you can see here, it's very intuitive. if else, here's my test condition. If it's true, do this, and if it's not, do that. So that's what we got here. So check to see if the combined data.combined ticket is equal to an empty string. Now, I don't know for sure if there's an empty string or not, because you can see there's 929 levels. But since this is a factor and an empty string is a valid factor level, this is basically some defensive programming. And basically I'm saying, look, if you happen to run into a ticket string that is empty, that is the factor label is blank, just put in an empty space instead and return that back. Otherwise, give me the results from the substring call. Okay, now as we were just talking about with substring, the if else statement is a function call statement is also vectorized. So it knows how to go through and say, okay, look, this thing here that I'm operating on is actually, that's not one logical test, it's 1,309 logical tests, which allows us to go basically iterate over the entire 1,309 tickets in one line of code and then cram the results into this new variable that we're calling ticketFirst.char. Okay, so what I'll do here is I'll go ahead and run this as well as the unique function. We've talked about that before. And all the unique function does is say, look, you know, if you give me, whatever you give me is the parameter to the call, I will return you back the list of the unique values. And you can see here that my defensive programming for checking for an empty string was unnecessary, but you know, it's okay. And I get back all of the individual unique items, right? So this is all of the first characters of every single one of those 1,309 tickets. Okay, great. So now I've got a much smaller set. So that's reasonable for me to actually consider a factor variable. You know, there's maybe 10, 15, 20 of these values. So what I'll do is I'll actually convert the variable we just created, this ticketFirst.char, ticket.first.char, and I'll make it a factor. We've seen this before, but I'll go ahead and pull it up just for the sake of completion in the help system. As factor is basically a utility function that allows you to convert an array of things, a list of things, a vector of things into an R factor variable. And then what I'm going to do is I'm just going to stuff it into a new variable that I'm going to add called, appropriately enough, ticket.first.char, and just assign that variable into the data.combined data frame. That'll just make some of these graphic analysis that we're going to do easier. Now, as you've seen over and over again in this video series, we're going to use ggplot2 to visualize our data because it's a great way to start doing these data analysis, especially when you're looking at things like classification, because visual representations of the data are a good way for you to see patterns that could potentially be useful in training your models. So go ahead and run that. And as before, I'm going to just go ahead and zoom in because bigger graphs are better than smaller ones. Okay, so here we have just a really super high level plot that says, look, along the x-axis, just give me all of the values that we pulled out. So these are all the first characters of all the various tickets, the unique values. And then give me the counts, right? So I get the overall sense of the distribution here. So there's a lot more tickets that start with 3, 2, and 1 than anything else. And then lastly, these are color-coded based on survival rates. The orangish color is the fact that folks perished, and the turquoise color is that people survived. And what you can see here is that, in general, you know, it looks like slightly more people than not survived if they had a ticket beginning with 1, maybe close to 50-50 here with 2, maybe a quarter or so, 3, and then, you know, it's a mixed bag. But P looks like it's pretty good. You know, if your ticket started with P, you more than likely survive. So this is on the surface here at this very super high level. This is some signal that maybe there's some structure in this data that allows me to help me decide whether someone survived or perished on the Titanic based on the ticket. Now, that may not be exactly intuitive. Sometimes in business problems, believe it or not, things that are counterintuitive actually are pretty powerful in terms of prediction. And that's one of the big differences, arguably, between applied data science in the business world, and more purely scientific pursuits like statistical modeling and econometrics. Those latter two disciplines are really focused on not only modeling and modeling accurately, but they're also very focused on providing explanations as to why things are the way they are. For example, in econometrics, hey, what is the effect? What is the statistically measurable effect of interest rate changes on unemployment, the economy, prosperity, whatever you can name, right? So those two pursuits are much more focused on having statistically viable, statistically valid ways of explaining things. Whereas oftentimes in the business world, in applied data science, your business customers or the people that you're working with don't care. As long as the thing works, oftentimes they're not necessarily interested in the explanation. They're fine with it just working. So the reason why I mention that is because maybe sometimes you'll come across something in your data analysis that doesn't match your intuition, but yet is surprisingly effective. And if your particular problem at hand is such that you don't need to explain why your model works, you just need to show that it does work, go for it. Just roll with it. But I'm a little skeptical here. So what I want to do is let's do another plot and drill in a little bit. So this first plot that we have right here is just a high level, right? All the tickets for all of the training set, and saying, look, okay, what are the relative counts of each type of first character for each ticket, and what's the relative proportion of survival rates? But let's go ahead and drill in and pivot that all based on P class, which is the class of where your first class, second class, or third class customer, essentially the quality of your accommodations aboard the ship. Now we can see here a plot where we've broken it out by P class, right? So this is the first class passengers, the second class passengers, third class passengers. And then you'll see the duplicate range of all of the various first characters of the tickets. Now this starts to tell a more interesting story. For example, oddly enough, or maybe not, depending on the business rules at the time when the tickets were issued, most folks in first class by far and away had tickets of type 1, or started with a ticket number of 1. And as you can see here, those folks disproportionately seem to survive. Even more so here on P, which is the second most common. And then first class, or excuse me, the second class starts with a number 2. And you would think, oh, maybe there's a pattern here that first class, lots of people's tickets start with a number 1. In second class, lots of people's tickets starts with ticket number 2. But then you can see here in the third area of the plot that kind of gets shot down pretty quick. Whereas this, because you can see here, the single most common ticket number starts with 2 here in third class. So that pattern doesn't really exist. Moreover, you start to look at these things and you start to wonder, well, there's an awful lot of turquoise here and here as compared to here, but we knew that already. We knew that people in third class, not surprisingly, unfortunately, perished at far more often than folks in first class did in general. So you would kind of expect to see that most of these ticket bars would be predominantly turquoise in first class anyway. So this is probably worthy of one more click down. So what I'm going to do is take advantage of what we've done to date, which we saw that the most predictive data that we saw, the most predictive variables that we've seen so far are the combination of P class and title. So let's take that pivot here. Okay, and it takes a second to run, and we'll go ahead and zoom in, and I'll just full screen that. Okay. Now this one's a little harder to read, but I think it's also a little more explanatory on whether or not tickets actually have any sort of underlying structure, any sort of signal that allows us to detect whether ticket was a good way of knowing if somebody was likely to perish or survive on the Titanic. And as you can see here, it's kind of not, because we see at a meta level the same pattern, right? So if you have the title of master, which corresponds to a boy, a non-adult male, you're blue, or turquoise, which means you survived, which we saw before. Miss, which ostensibly maps to uh, unmarried adult females as well as female children, girls, was vastly green or turquoise as before, so that's not really surprising. And generally speaking, what this shows me is that there's not much structure here. There's not much signal in the ticket variable, which matches to our intuition. As I said before, sometimes that's not the way it works, but more often than not, your intuition is probably pretty good. And always double check it with the data, of course. But here we've got a situation where the data seems to match our intuition. So what that means is that I probably wouldn't want to use ticket in my modeling, at least in the beginning, because if there's not a lot of signal in the variable in the data in question, it doesn't make a lot of sense to put it in the model, and that's because Occam's razor is very applicable to applied data science and modeling in particular, which is, all things being equal, you tend to prefer simpler models than more complicated models, and that's everything from the nature of the algorithm itself. So, for example, logistic regression, which is a classification algorithm, is far simpler than a deep neural network that you're using for classification. If they both tend to produce the same accuracy on your cross-validation, you probably would tend to prefer the logistic regression one because it's going to generalize better. The simpler models tend to perform better on unseen data in the future than more complicated models in general. Again, Occam's razor. Same thing with the data that you use to train the model. In general, if you can get the same level of performance in your cross-validation with smaller data sets, that is, less rows or maybe less columns or maybe both, that's probably good because that generates less complicated models, which again tend to generalize better to future unseen data. Okay, so tickets out for the time being. Maybe you would add in back later, but at least for the time being, you're probably not going to put it in the model. Okay, so next up, let's talk about the fares. So this is the amount of money that each of the passengers paid to ride on the Titanic. Now, I'll start with the intuition that I would have here, which you probably do as well, which is, hey, wait a second. There's probably a very strong correlation between P class, first class, second class, third class, and the amount that you paid. Typically speaking, first class tickets are going to cost much more than third class tickets. Just like in modern airlines, first class costs more than business class, and business class costs a lot more than coach or economy class. Same type of deal. But we want to be thorough. We don't want to leave any data on the table that could potentially help our model, so we should take a look at it. So what I'm going to do here is, first and foremost, just take a look at the summary of the fare variable as well as spit out the length of the number of unique values. Okay, so fare is obviously a numeric variable. I assume that, but of course I could have double checked that explicitly by just typing out, right, the structure, and right there it would say, oh, okay, it's a numeric variable. You got 1,309 of them, and here's the first few values. But I just assumed that it was a numeric variable and asked for the summary statistics on that, and that's what I got here, which is, okay, some folks didn't pay any fare at all. That could be potentially interesting. Fully 25% of the fares, right, the first quartile are I'm assuming pounds here because I believe the Titanic was run by an English line, so say 7.896 pounds sterling or less. And the median value is about 14.5 pounds sterling. So basically fully 50% of the passengers in the data paid less than 14.5 pounds. But you'll notice that the mean is actually more than double the median, which means that this distribution we would expect to be skewed to the high end. And you have evidence of that as the max value of 512, over 512 pounds. That's going to certainly skew things. So that could be potentially interesting. Not surprisingly, we did the length of the unique values of fare, and there's a large number of them. The reason why I did this, as I illustrated in the previous video, is that sometimes even if you have a numeric variable, if there's a small number of unique values in your data set, you could potentially transform that into a factor because that may be useful for you for certain analyses, or it acts as a natural binning mechanism. Rather than actually trying to create numeric bins, you can just use the actual instances of unique values themselves as bins to help with various types of algorithms. But in this case, there's way too many unique values, so I don't really see any value in that. So once again, we go to ggplot to say, look, our intuition says that we're going to have kind of a skewed distribution here. Let's validate that that in fact is present in the data. And you'll see here a warning message. This is new for ggplot2 compared to the videos in the past. And this is basically saying, hey, I tossed out a value, and that's because there's a 1 NA. I didn't really, 1 NA out of 1,309 values isn't something I'm going to necessarily spend a lot of time worrying about. So I just said, okay, ggplot, go ahead and take care of it, and it just tossed it out. All right, let's zoom in on that. And you can see here, here's the distribution for the fares. And we've got this outlier way out here, 512 pounds. But you'll notice that there's, some numbers here going from 100 pounds on up. It's not, obviously it's a, almost an exponentially declining distribution, but you can see it's got a pretty long tail here sliding out to the right. And, as you would expect, a large bulk of the folks on the Titanic corresponding to third class, more than likely, didn't pay a whole lot for their tickets, because we saw from the summary statistics that fully half of people paid 14.5 pounds or less. So very long distribution, long-tail distribution here. Okay, so that matches our intuition based on the summary statistics. It's good to know that there's not many people are out here paying 500. So that must have been one heck of a room, cabin, stateroom, whatever that they got on the Titanic for that kind of outlier. So let's drill down again to see if it's got predictive power. And what we're going to do is just jump into the plot that we've seen before, which is grab the training data, because those are the ones with the labels, and those are records 1 through 891. Facet wrap, or essentially break out, pivot the plot based on the combination of p-class and title, and fill in the bars with the colors for survive. So this is basically the thing we've seen many, many times so far in this video series. I will zoom in. I know this plot's hard to read. I apologize for that, but it's still visible enough so you can start taking a look at it. You can say, okay, some things at a meta level don't really surprise us here in this plot. For example, those with the title of Miss that happen to be in first class, very, very little orange, all turquoise for the most part, which is exactly what we expect. Same thing for Master in first class, the title of Master in first class. And then, some breakouts here. Misses in first class, so this would be adult married women. Almost all turquoise, just a little bit of orange, again what we would expect. And then going all the way down to adult males in third class with the title of Mr. Yeah, not too great. There's a small blip here where you say, well, is there some signal there? Maybe, but that would be, again, I would be worrying about, look, if I actually tried to make my model pick this one piece of data out and saying, oh, if you happen to be an adult male in third class and you happen to pay this exact dollar amount, let's say, for your fare, and I'm going to say, look, most of the time you survive, I would be worrying about overfit. And what I mean by overfit is it's entirely possible to build a model that will 100% always predict based on your training data correctly every single time. You can imagine, if you will, and I've talked about this in previous videos, is that I could literally write an algorithm that says, if your name is this, I know you survived. If your name was that, I know you perished. That would be 100% accurate for your training set, but it would not generalize at all, because you would, well, what if you had Billy Joe Jim Bob come in, and Billy Joe Jim Bob is not a name that was in your training set? You wouldn't know what to do with that. Your model wouldn't know what to do with that. And that's overfitting. So creating a rule, let's say in your model that says, hey, if you're an adult male in third class and you paid this for your fare, you are, let's say, 75% likely to survive. And then you just do a simple random number generation and then how that rolls, and that's how you predict. It's probably an instance of overfitting your data. So what I'm seeing here in general is nothing that really speaks out to me that fare is going to add any signal. It's going to add any additional predictive power to my model over just simply picking the class, right? Take, for example, adult males in first class. These fare distributions don't really tell me, unless of course you're way out here with the outlier, right? So this guy out here paid over 512 pounds for his ticket, and that probably corresponds to using the axes to exactly one person, maybe two. If I had a rule that just fit this, that would, again, I'd be risking overfit. So I would worry about using this instead of P class or in addition to P class. I don't think there's going to be adding a lot of value. So as with ticket, I think in the beginning, we're not going to be using fare in our initial modeling efforts. Now, of course, that's my opinion. So part of learning data science is to find your own way and the own styles and patterns and techniques that you like. So there you have it. Okay, so we took a look at fare, we took a look at tickets. Now let's take a look at cabins. Now, intuition here would be potentially that cabin would look an awful lot like class, because you would imagine that the cabins are denoted by some sort of nomenclature that implies what deck and therefore what class you're in. Most typically, if you're in third class, you're probably below decks, maybe even potentially below the water line, maybe of the ship, so you won't actually have a porthole or a window or anything like that. Whereas first class, you're probably up on the upper part of the ship, upper decks. Same thing right now in modern cruise ships, right? You get on these big cruise ships and same thing, right? Usually the more expensive cabins, the higher class cabins are up and above in the sunshine, and the cheaper cabins are down lower in the ship. Okay, so we can go ahead and just say, hey, what's the structure real quick to confirm? And we can see here that the cabin variable is a factor with 187 levels. So again, that's probably not really a factor variable. We should probably turn that into a string variable because 187 levels is really high. And by the way, certain algorithms, in one algorithm in particular that is extremely useful and that we'll be using in this video series is a random forest. And the default random forest implementation, the de facto, I should say, the random forest implementation in R cannot handle factors with more than 32 levels. So this is a problem on two levels, no pun intended. First is, it doesn't make any sense because at 187 levels, it's probably a string variable. And secondarily, it's not going to work with the random forest algorithm anyway, so we should probably just change that to characters. So what we've got here is same code that we saw before with ticket. Let's go ahead and transform it from a factor into characters, and then stuff that back into the cabin variable on the data.combine data frame. And then spit out the first 100. And why I picked 20 up above and 100 this time was purely stuff I did offline before recording this video, saying, okay, how many would I need to take a look at to get a high-level sense of the data? And it turns out with cabins, unfortunately, as we'll see in a second here, you need a lot more dumped out. And now you can see why, because a lot of records are blank. So that's why I needed a lot more than 20. Okay, and I just played around with it. There was no magic to pick 100. I just kept increasing the number until I got a good sense of what the data looked like. And this output here gives us a lot of good information about this particular variable in the data frame. We can see here a number of things in particular. First, as I mentioned already, lots and lots of empties, so we'll need to worry about that. And we also see some nomenclature where you have kind of what you would expect is to say, look, we have a number which is probably cabin number, which is probably based on this idea of a deck F or G or C or D, and then a number, right? This is the opposite of what you would see, obviously, on a commercial airplane these days, but it's a similar idea, right? Where in a commercial airplane, you have row and then seat number, so it's exactly the opposite. It's number and then letter, but here you have letter and then number, which is probably indicative of cruise lines. Not being an expert in that space, I'm just guessing at that. Another thing that we notice here, which is kind of interesting, is that you can actually have multiple cabins listed. So this entry and this entry are probably from the same group of folks, I would imagine, and they have 3 cabins, C23, C25, and C27. These folks here have 2 cabins, D10 and D12, so that's interesting. So now we've got a couple of different pivots here from a structural perspective. Not only do we have the idea of potentially, if these letters represent decks, which is highly likely, that may actually be potentially predictive, right? Because the intuition would be is the further you were up the decks, the higher you were in the ship from the waterline, the closer you were to the lifeboats, and also you were probably a more wealthy person, a more influential person. So all that probably combines to say you probably had a higher survivability rate than folks that were below decks. Now, what I'm wondering, and I don't know for sure, is this indicative of folks in third class? As I recall, I think I remember seeing a picture one time of third class accommodations on the Titanic, and I think they were like, some of them were rooms with like multiple bunks. So maybe this is indicative of third class potentially. And since, as we know, there's a lot more people in third class than they were in other classes, maybe that may reinforce this idea. But anyway, this alone probably won't give us a lot of structure. So what we're going to do is actually massage this data a little bit, and as we did before with ticket and fare, see if there's anything to it. So the first thing I'm going to do is I'm going to take all of the cabins that are blank and just replace them with a U for unknown. And you can see that here, right? Again, which, we've talked about that previously. It's like a where and a SQL clause. So this is like saying, hey, go through the data frame and find me every place where the data.combined data frames cabin variable is equal to a blank string. Grab me back all of those indexes so then I can index the variable, or the data frame, excuse me. So that gives me all the indices where the cabin is a blank string, and then grab the cabin variable off of that and then cram a U into it. We'll do that, and then just to double check that the code worked correctly, we'll run that again, and you can see here all the blanks that we saw up above are now U's. Okay, great. And then we're going to just take the first letter again, and that makes some sense because at a high level, right, if there's any signal in this variable, it's going to be first and foremost denoted by the dex, most likely, because the differentiation between, hey, the survivability between cabin C123 and C103 would strike me as being something that may be prone to overfitting. And you're going to hear me talk a lot about that going forward in the video series. You don't want to overfit. Overfitting is bad, 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 bad. So I'll just start with creating a new variable called cabin first char. That's just basically the first char of every cabin. And I don't need the defensive programming that we saw earlier with ticket because I already took care of the blanks up here. So let's go ahead and run that piece of code. Great, and then I can check the structure. I made it a factor and it's got nine variables. This is great. I can also use this thing called the levels function if I actually want to explicitly run all the levels out. Oops, got to actually run the whole line, Dave. Okay, there you go. And we see here, great. Here's all of the expected labels that we have on our new factor variable. So deck A, B, C, D, E, F, G, T, and then unknown, or U. Great. So let's go ahead and cram that into a variable that we'll add onto the data.combined data frame. As before, that just makes some of the ggplot a little easier. So we'll just run that real quick. Boop. And we'll, as before with ticket, we'll do a high-level plot. This is just basically saying, look, in general, For each level of this cabin.first.char, as denoted here by the X on the code, just create a bar chart. And then within each of the bars, color code that based on survival rates. So nothing fancy. Same thing we've seen many times before. I'm going to zoom in on that. And here we can see something potentially interesting, which is something that's not necessarily all that interesting, which is, these survival rates on the first blush seem interesting. We should probably click down, and we will, but, looking at all the data, as much time as we've been spending with the data now, this is where, as I said before, it starts to speak to you. I can look at this plot and I can go, well, nothing jumps out at me really, because yes, individually each one of these bars, a lot of them seem to be disproportionately survived. But I already know that these more than likely correspond to the classes anyway. I don't know for sure, but seems to me, just based on relative proportions of the population, I know that very small numbers of folks, relatively speaking, were in first class and second class. And if the decks are, a deck happens to be the top level deck, which is probably likely, and that corresponds to smaller numbers of folks, then yeah, it probably means that these folks up here are probably first class, and these folks here are probably in second class, and these folks here are predominantly in third class, and the proportions of survival rates are kind of what I already expect, right? Because I've been spending so much time getting steeped in my data, and that's so important. But we'll drill in anyway, because we're data scientists, and we don't want to run on our guts. We want data always to drive what we're doing. So here we go. This is the next click down, which is, okay, look, let's validate our intuition that the lower lettered numbers actually correspond to first class, because they're higher in the ship vis-a-vis the waterline, and that's borne out right here. A through E, obviously very much predominantly in first class, with very few people, relatively speaking, with no tickets in first class. And then you start to see a big shift here in saying, oh, okay, well, the vast majority of those folks with no tickets defined are in second and third class. And as we would expect, as you go through the upper letters, they're predominantly focused on the lower class tickets. So here you can see D, E, and F. Predominantly you survive, but that's not surprising because you're in second class. But if you look at E and F here, not so good, but that's third class. So again, that's interesting. So we'll click down one more time, but this is starting to jive with our intuition, which says, look, maybe cabin's not going to be super helpful for us, because there's a strong correspondence between the cabin, the decks, and the class anyway. And as we know, class was obviously a very powerful predictor of survivability. Okay. So now we'll just run this one, which is just to be 100% thorough, which is our plot of P class and title. And again, not seeing a lot here to really shock us, which is there's no real discernible trend, right? Okay, so for example, adult males in third class. If you were the lucky one dude, looks like, that had an E ticket, you survived. If you had an F ticket, or maybe it's a couple guys here, you didn't survive. If you had rules in your model specifically for those instances, you're probably, I should say probably, very, very likely that you're going to overfit. And over here, this distribution makes a lot of sense, because we know already that, generally speaking, adult males in third class didn't have very good survival rates. And the rest of this is, there's just not really a lot of signal here that I'm seeing, right? First class adult females, they all survived, basically. Okay, we already knew that. So I won't belabor that. But the one thing that we identified that maybe we should check that could be interesting was, what about folks with multiple cabins? That would probably, the intuition would be is that if you've got multiple cabins, you're probably pretty well to do, right? Because if you don't have a lot of money, you're going to try and probably cram as many folks as you can in a room, and you're not going to necessarily have more staterooms. Oh, and that's either a reflection of you just have a lot of money and you can afford more space, or maybe you just have a larger family. Either way, you're talking about more pounds, so more wealth, intuitively more likely to survive. But let's check it out anyway, because again, we're data scientists and that's what we do. So here we have another interesting line of code here, again showing the power of R for data manipulation tasks, which is why personally I prefer it over, I do work in Python, but I prefer R generally speaking for this reason, is this expressiveness of the language. So we saw if else already. We know what as factor is, so I'm not going to belabor that. So let's take a look at string detect. So pull that up. So string detect is a function in the stringer package, which we talked about, as I recall, probably in the first video. I think we introduced stringer, which is a package, as I believe it's written by Hadley Wickham, who is a guru, an author of many, many commonly used and powerful packages in R. This one's for making string manipulation a little easier. And specifically what we're going to use this for is to go through the cabin variable of the data.combine data frame, excuse me. And as with other functions that we talked about, string detect is vectorized, so it knows automatically that we're talking about 1,309 string values. So we're asking it to do 1,309 detections. And we're saying, okay, look at all the cabins and tell me if you can find a blank space in the cabin. Because as we saw from the earlier data, went too far, we can see formatting wise that in the case of multiple, in general, the case of multiple cabins, you'll see a space. Now, we got some dirty data here, ostensibly where we have an F space G7. I think that's okay because we're just doing a high level analysis right now. If we decided that we're going to use multiple cabins as a predictor variable, we would probably want to do some more in-depth analysis and data cleansing on this variable. But for right now, I'll just assume that this is actually 2 cabins, even though this one is not fully filled out. It's just an F. And then, of course, the if-else then takes that as a test and says, okay, if a space is there, then return a Y, otherwise return an N. Yes, it's a multiple cabin, or no, it's not a multiple cabin. And then we make that a factor and we cram it into a variable that we're just going to add directly on the data.combine data frame called cabin.multiple. All right, run that. And now we can plot it. So I'm just going to skip, because I don't want to belabor this idea of drill downs, because we've already seen it twice now, that we're just going to go ahead and plot this bad boy and see what's going on at the lowest level of grain, which is our pivoting on P class and title simultaneously. Okay. And so here we have it. So unfortunately, we tend, at least in the States, we tend to think of things as yes and then no, but by default, ggplot orders these things in alphabetical order. So this is the no's and the yeses, so just keep that in mind. For those of you outside the States, maybe that's not going to be an intuitive problem. Okay, well, what we can see here is, again, nothing that really pops out at us. So, as we would expect, most adult males in third class do not have multiple cabins. Not a shocker, and very few of them survive. Well, we already knew that. On the flip side, we can see that in general, on the yeses, let's say the yes columns, which is the second here, not a lot. This is a very rare thing. And again, given the rarity of it, I would be worried about its generalizability. That is, I would be worried that if we coded rules specifically to this variable at this point, that we would be prone to overfitting. So not seeing anything here either, at least on the first pass. Maybe we'll revisit it later on, but I think for the first pass of modeling, I don't think we'll need to worry too much about that. Okay, so lastly, and this will clear us out of all of the first pass of the variables here, is let's take a look at where you got on board the Titanic. This is where you embarked. Okay, so what we see here is the structure of the data.combined embarked variable, which is a factor of 4 levels. And looking at the levels of that factor, we can say that some of them are blank, C, Q, and S. Okay, so if we tab over to our definition here, we can see that C corresponded to Cherbourg, Q was Queenstown, and S was Southampton. Intuition is that I don't think where you got on the boat is really going to matter. Now, statistically, maybe there's a high correlation between folks of certain economic backgrounds being disproportionately embarking from certain locations, but I think that would be a bit tenuous. But let's check it out just to make sure that we're doing our due diligence. Since there's only 4 levels here and one of them is blank, I'm not going to worry about populating that with like something like a U, because I think this is fine. So we're going to just go ahead and plot this and take a look at it. And again, we'll just go to the base level drill down, which is the pivot of P class and title. Okay, and there you have it. We have all the folks here, so you can see that this one here is unknown. This is Cherbourg, Queensland, or Southampton. And again, not seeing anything that really jumps out at us, which matches our intuition, which is, interestingly enough, maybe that, as we talked about before, adult males in first class disproportionately came from only Cherbourg and Southampton. No one came from Queensland. Looks like not many folks came from Queensland, but what it looked like would be is that, if anything, people the signal that you would pick up by focusing on embarked would be, look, if you happen to embark from Queensland, you're way disproportionately likely to have been a third class passenger. I mean, that's probably the single most powerful thing that I've noticed, is that that jumps out at me, right? Because there's very few folks from in the higher classes, first and second class, that come from Queensland. So, but from a survivability, which is what we're actually interested in predicting here in this case, there's not much going on, because as we know, if you had the title of Miss in first class, you predominantly survived, which is what this is showing. If, for example, if all of the orange here was in Queensland, that would be interesting potentially, but again, you'd have to weigh that against the risk of overfitting. So again, I would say in our first pass for modeling, embarkation is not going to be that important. So to summarize, if we look at the data combined here, and this has all of the feature engineering work that we've done to date in it, we're going to use P class. We know that's super important. Name is not particularly useful, as we saw in the first video. Sex, we know we're going to get now from our derived title, so we wouldn't use sex. We've also determined that age has way too many missing values, and we don't want to use it if we don't have to. So we found that title is a good combination. It's a good proxy for the combination of sex and age, making it a potentially powerful single feature to use. We've taken a look at SIBSPA and Parch, and we know there's some stuff in there, so we'll probably take a deeper look at both of those in the upcoming videos. Ticket, we've ruled out. Fare, we've ruled out. Cabin, we've ruled out. Embarked, we've ruled out. Going down, we know that, as we've talked about, title is extremely important, along with P class. Those two things are very, very predictive together. Family size looked like it had a lot of potential as well. One of the things we'll take a look at in future videos is potentially is the ratios between family size in SIBSPA and PARCH, for example. There may be some signal out of that. Ticket first char we ruled out, cabin first char we ruled out, and cabin multiple we ruled out. So this is the end of video 3. We've done a lot of goodness here. Hopefully you're finding this useful and starting to see some of the method and the madness in the approach. I look forward to the next video where we're going to dive in deeper on a smaller subset of our features and see if we can get to a point of building a model. So until next time, happy data sleuthing.